Yep, today's a good notes day. We're going to cover a lot of stuff. So you will want notes, or else you'll spend a lot of time looking at the lesson throughout the week, reviewing through the lesson. It's easier to just have it all on the note page. It's going to be a busy week already. A busy week. So today is Tuesday. Friday is an A day, so we only have class today and not Thursday. It's like, what? We don't have class. This is the only day we have class this week. That just occurred to me as that sentence was forming in my head right there. That today's the only day we have class this week, because Thursday is the PSAT for sophomores and juniors, and seniors have work keys, and freshmen have some community service stuff. So nobody has class on Thursday except for eighth hour, but that certainly doesn't affect us. We're 0 hour. So Thursday is going to be a little different. And then after being all day here for testing, then we get to stay here for parent teacher conferences. Yay. So Thursday, I'll be here from like this time in the morning till 7:45 at night for parent teacher conferences. Yes, we just had them 3 weeks ago, but we're scheduled to have them again. So yeah, Thursday, bring your parents on up there. But anyway, so yeah, it's a day Friday, so that means this is our only class because of the testing that's happening on Thursday. So we'll just have to enjoy it while we got it before all the PSAT stuff starts up. But anyway, today's a great day to have a pencil and have notes. Sharpen your pencils. We're got a lot to cover. We're going to cover 5 theorems today. We are going to be busier than a one-legged man in a butt kicking contest. So let's get things going here. So we're done with the first 2 modules. We did the first 2 lessons last week on polynomial and synthetic division. And now we're looking at theorems of algebra, including the rational root theorem and Descartes' rule of signs. He was a French mathematician from the 1700s, and he came up with some pretty cool stuff that he added to the world of mathematics. But 3.03, 3.04, let's jump into it. Like I said, we got a lot to cover with this. So, theorems of algebra. Here we go. All right, so most people, even if they're really not even mathematically minded, they've heard of the Pythagorean theorem. Most people say, "Oh yeah, I've heard of that. That's something with an A or something." Yeah, a squared plus b squared equals c squared. Right? We had the Pythagorean theorem in geometry. It only applies when you have a right triangle, which means a triangle that has a 90-degree angle. That's the only time that theorem's even useful. But that's the one that people remember: a squared plus b squared equals c squared. The Pythagorean theorem. But in math, there's a lot of theorems. What is a theorem? A theorem is a statement, not necessarily mathematical in nature, that's proven by experimentation. In mathematics, you prove theorems. Once they're proven, they're called a theorem. Before that, they're a postulate or many other names for it. It's a theory or something. Let me mention this real quick. If you're interested in theorem and love proving things in mathematics, the Clay Institute, big math place, in the year 2000, put out the 10 most important mathematical concepts that still have yet to be proven, and they put a prize on them. So if you can prove one of those 10 mathematical items that have not been proven yet, $1 million each. They put a prize on them if you can prove it. And so they list all kinds of different postulates and different things. You can look it up, the Clay Institute, the Millennium Prizes. And of those 10, one of them has been proven since, and some of them are like from the 1700s and 1800s, and some of them are more current math theories. But one of them was proven in like 2004, I believe. And I think it was a Russian mathematician. He wrote the proof, and the proof was like 167 pages. Took 167 pages to finally prove. And I heard he turned down the prize. Now, why you would do that, I don't know. But but I don't know. So I don't know if that's true or not. But yeah, one of the 10 have been proven. There's still 9 out there waiting to be proven because they think they're that important in math that we really need someone to come up with a proof. So there you go. If you want something to strive for as a mathematician, $1 million prize is not a bad way to go. All right, we're going to learn what the key features of a polynomial can be found using the fundamental theorem of algebra and the factor theorem. And we're going to look at the remainder theorem. So we got 3 theorems here: fundamental theorem of algebra, factor theorem, remainder theorem. So let's start out with just the fundamental theorem of algebra. So the solutions to, let's say, a quadratic equation, you can find that by doing the quadratic formula, completing the square. You can factor it sometimes. You can graph it. There's many, many ways we know to factor a quadratic equation. You've done a lot of those. And if you look at the discriminant, b squared minus 4ac, discriminant, something that we look at in Algebra 2 back then. It's part of the quadratic formula. If you'll recognize that b squared minus 4ac, that's the part that's on top of the fraction underneath the square root of b squared minus 4ac. If that is a perfect square, then we know you can factor the quadratic equation. If you calculate that for this equation, x squared plus 11x plus 18 equals 0. So a is 1 because there is no coefficient for the x squared. B is 11, C is 18. If you calculate this b squared minus 4ac, it'll turn out to be 49. 49 is the perfect square, right? Because you can take the square root of 49 and it's 7 or negative 7. So that tells you you can factor the quadratic equation and you'll get 2 very nice numbers. In this case, when you factor that, you'll get 9 and 2. X plus 9, x plus 2 is how that factors. And if you graph it, that gives you those solutions also, because the zeros where it crosses the x-axis is at negative 9 and negative 2 on the x-axis. So that tells us also that x plus 9, x plus 2 are the factors of that quadratic equation. So graphing is a wonderful way to find the zeros of this equation. So pay attention to where it crosses the x-axis, because the x-intercepts are the real number solutions when a quadratic equation is set to 0. That's why it's called zeros of the function. Notice I said real number solutions, because it could be that your quadratic equation has no real solutions and only has imaginary solutions, right? If it doesn't touch the x-axis, if it has a plus 1 at the end that raises it up 1, it may not touch the x-axis at all. And so then your solutions are imaginary. So graphing only shows the real number solutions. So there are 2 zeros to this function, and the degree of the function is 2. Could there be a relationship between that? Absolutely. Let's look at, starting off, the fundamental theorem of algebra. That's a lot to write, but I'm going to put it all on our notes here. Okay, the fundamental theorem of algebra. What does the fundamental theorem of algebra say? Well, it's probably easiest to, instead of writing out exactly what it says, is to give examples. If we have this equation, 2x to the third plus 5x squared minus 1. Or if we have this example, let's see, 4x to the fifth minus 3x to the fourth plus x squared minus x minus 2. Or this example, f of x equal 12x to the eighth minus 7x to the sixth plus 4x to the third plus x plus 16. Looking at all of these and using the fundamental theorem of algebra, we can tell how many zeros are solutions that each of these have because of the fundamental theorem of algebra. This will have 3 solutions, or zeros, as we might call them. Now, it's very possible that some of those are imaginary zeros. They may not graph and show 3 zeros on the x-axis, but there are 3 solutions. This one will have 5 solutions or zeros. This one, well, guess how many they have? Well, the reason we know the fundamental theorem of algebra tells us there are 3 solutions is because the largest exponent is a 3 and a 5. So we can guess how many the last one's going to have by looking at the pattern. 2x to the third is the largest exponent. This one, 8 is the largest exponent. So this will actually have 8 solutions or zeros. So the fundamental theorem of algebra. Here we are in Algebra 3, and we're finally getting down to the fundamental theorem of algebra. Fundamental, the basic, the very core of algebra says whatever the highest exponent, the highest degree of your equation will tell you how many solutions there are. It will tell you how many zeros that the equation has. That is the fundamental theorem of algebra right there. So with that, let's do some math, because we want to look at some other theorems while we're at it. Let's see what the lesson said about the fundamental theorem. It probably put it in some good mathy terms. Let's see. The fundamental theorem of algebra. This theorem generally states that the number of zeros, and this is important, either real or complex. Remember, complex means it's imaginary. It'll be like 3 plus 2i. Is equal to the degree of the polynomial. There's the mathematical definition of it. If you like math definitions in your notes, there it is. This theorem states that the number of zeros is equal to the degree of the polynomial. So if the largest exponent is the 4th degree, that's a 4th degree polynomial, and it'll have 4 zeros. It says, let's look at f of x equals x to the third minus 12x squared plus 35x. If you graph that, you see 1, 2, 3 times it crosses the x-axis. And it's an x to the third equation. So we would expect it to have 3 zeros. In this case, all 3 zeros are real zeros because we can see them when we graph it. There are no imaginary zeros, only real zeros. But that gives us the solution of the zeros to this equation right here. And it's at 0, 5, and 7 are the zeros. So 3 x-intercepts. All right, so they give us some examples here. Determine the zeros. You can determine the zeros of this by graphing or by factoring. It's a quadratic equation. So I'll leave that video because we don't have time to watch all the videos today. But this one, it factors this one to find the zeros of -4 and 7. This is the one I want to look at because sometimes people look at this and they're a little bit blown away by, oh, that doesn't look like a normal equation. It's got everything x plus 2 times x plus 2 plus x plus. That's just the factored form. That's a 4th degree. It's a 4th degree equation because if you multiply those 4 factors back together, the largest will be an x to the 4th because there's 4 x's. But it's already factored it for you. And it actually makes it very, very easy to find. It's only 37 seconds. We'll watch this one. To find the zeros because it's already factored. Sure. Oh, and it doesn't even have any sound to it. Let's go back and see what they did. They basically set it equal to 0, those 4 factors. So after it sets it equal to 0, then you look at each factor individually. Say, okay, which one? If this was equal to 0, or if this was equal to 0, or if this was equal to 0, or if this was equal to 0, you come up with the 4 solutions: -2, -2, 1, and 3. So it has 4 solutions, but 2 of them repeat. -2 is a solution twice. So when you identify the zeros, they're -2, -2, 1, and 3. And since -2 appear twice, in math, we call that a multiplicity of 2. So we would list 3 solutions. We would say there's a solution at 3, there's a solution at 1, and there's a solution at -2 having a multiplicity of 2. It just means it's a multiple solution. of 2. There's 2 of them. It says if we had a function that had 3 zeros that are all the same, maybe they're all 5, x equal 5, x equal 5, x equal 5. We said the solution is 5 with a multiplicity of 3. We can just use that multiplicity for whatever number we need it to be based on the solutions. Then it uses a graph to confirm that. So it says, okay, so if we put that on a graph, we should see a solution at -2, 1, and 3. Now notice the graph does something different at -2. When there is a multiplicity, in fact, we can go over that right now. That's something I waited to the end of class the other day to cover, but let's cover it early today. If we're graphing, here, we'll get some graph paper. And we calculate the zeros. All right, so when we have the zeros, and let's say we calculate a 4th degree equation, and we find the zeros are all real, and there's a zero of -4, -1, 3, and 3. This is a 4th degree. We said it was a 4th degree. So since that's even, this is an x to the 4th. Since it's even, we know that both ends are going to go up because it's positive. If it was negative, we know they'd both go down. But in this case, we said, oh, this is a positive. The first term is a positive. The 4th degree term is a positive. So it goes up on both ends. So we kind of know what the graph looks like a little bit. And we know where the zeros are. There is a 0 at -4. And there's a 0 at -1. And at 3, there's 2 of them. So what that means, if there are 2, say multiplicity, let's see. Multiplicity, even number, which is 2 or 4 or 6, et cetera, et cetera, et cetera. That's going to have a special effect when it goes to that 0. That means this one's going to start up in the air, going up towards infinity. It's going to go back here. And when it comes down to the 3, it's just going to bounce. So that is generally what this equation is going to look like. We could, if we knew the whole equation, we could know the y-intercept. Right? So if this is a x to the 4th minus 3x to the 3rd plus 2x squared minus x plus 2, we know the 2 would be the y-intercept. Because that's when x equals 0. Well, if x equals 0, this is 0, this is 0, this is 0, this is 0, and it's 2, this is your y-intercept. So we can make sure it goes through that point as well. So this is a rough sketch. This is not an exact graph. It's a rough sketch. And notice what happens here when a multiplicity is even, and it is here. There's two of those. It bounces. When it gets to the x, if it was coming up, it would bounce and go back down. It bounces. If the multiplicity is odd, which means 1st degree, 3rd degree, 5th degree, ... etc., ... Every time it's an odd multiplicity, which this is an odd multiplicity. There's only one of those. It crosses the axis. So multiplicity odd, it will cross over the axis. When multiplicity is even, there's 2 of those solutions. It'll bounce off of it. So that's kind of interesting. And we could actually calculate exactly what this equation is because we know the 4 zeros. So this could just be a guess, but we know it's actually x plus 4 times x plus 1 plus x minus 3 squared, because there's two of those. This is the equation of this graph. We could do the multiplication to put it all together, or we could just write it like this. So we know that's the graph that kind of looks like that. But this is the main thing to know. When multiplicity is even, it's just going to bounce. It's not going to cross the axis. It's going to bounce off of it. But anytime it's odd, first degree, third degree, fifth degree, if there's three solutions exactly the same, it's going to cross. If there's four solutions exactly the same, it's going to bounce. So it kind of gives us an idea what the graph looks like, really without knowing the entire graph. Okay, now I'm just dying to know how close we got. What's it really look like? Let's go to Desmos and see what it really looks like, because I just have to know now. So we could actually graph that equation using the factored form. If Desmos is going to cooperate and load this morning. Oh, here it comes. Okay. So our equation is f of x equals x plus 4 times x plus 1 and x minus 3 squared. Oh, it actually goes up a lot higher than what I did. Whew, look at that. The y-intercept is way up here, actually, at 36, right on 36. So it's a lot skinnier than what I had graphed it at. It goes a lot higher and a lot lower. But you get the key parts. Notice it does bounce at x equals 3. And it does cross at -1 and 4. So we got all the key things on there. So like I said, a sketch is not going to be an accurate graph. It's just going to give us the main points. And as long as we have the main points, we know that the ends both go up. We know where it crosses the x-axis. And if I had the actual equation, I would have known this was a lot higher than 2. It's up at 36. But it does go up on both ends. It does go up. Both ends go up. It's just a lot skinnier. All right. Let's move on. Here's more on the fundamental theorem of algebra. If you need more examples, it says determine the zeros of this: x minus 13 times x minus 18 times x plus 9. Well, that's really easy. You set all those equal to 0. So the zeros are 13, 18, and -9, which you can then graph and see -9, 13, and 18. But we calculate it here by setting them all equal to 0 to confirm those are zeros. And this is a third degree equation because you have an x times an x times an x, and that would give us an x to the third if we multiplied them together. So the number of x's with factored form tells you the degree of the equation. All right, let's look at the factor theorem. So the factor theorem, and we're going to use this equation, x squared plus 11x plus 18. So I'm going to write that one down on our paper. All right, I'm going to put it up on the screen, and let's talk about the factor theorem. So the factor theorem, our second theorem of the day, it says, okay, we were looking at this and we were factoring it, and so we said we're pretty sure that x plus 2 was a factor. And we can confirm that with what we learned last week. We can do synthetic division with 1, 11, and 18, right? And we would use -2 since this is x plus 2. And we would bring the 1 down, multiply by -2, add those together, multiply by -2, and we have a remainder of 0. So the factor theorem says if this is a remainder of 0, then this is a factor. If it's a remainder of 0, when we divide that in there, then this is one of the factors. And looking at our solution, since this was x squared, this is now x plus 9 with a remainder of 0. That's the other factor, right? We found the other factor by dividing this out and looking at the solution. So the two factors are right there. But the factor theorem says if this gives a remainder of 0, then this is a factor. Now, let me show you something cool that we didn't look at with synthetic division. There's another way to find the remainder without doing long division or synthetic division. You are kidding me, Mr. Brock. We did all that work and there's another way. Yes, there's another way. In math, there seems to always be another way, right? If we go back to the original equation, x squared minus 11x plus 18. And instead of dividing by -2, let's find f of -2. I'm just going to take the -2 that I divided by, and I'm going to substitute it into the equation instead. -2 squared minus 11 times -2 plus 18. So what we did there, we just took the -2 and substituted in everywhere there was an x. Instead of dividing it into it, we're going to do it this way. -2 squared. -2 times -2 is a positive. -11. Does that work right? Yes. No, it's not going to work right because I've got something off. X plus 2, -2. This is not doing like I did yesterday because this should be
It was plus 11, not minus 11.
It was plus 11. There's what I messed it up. I did the wrong equation. Plus 11. So yes, this is a -22. 4 minus 22 plus 18, that equals 0. Yeah, I wrote the equation down wrong. Thank you very much. Notice when we substitute -2 in, that tells us the remainder is 0 also. That's another way to do it. Instead of doing the synthetic division, I could have just substituted the number in. And that will do the exact same thing. And the factor theorem says, okay, since that equals 0, this is one of the solutions. -2 is one of the zeros. Interesting. So if we substitute -2 and get 0, that means -2 is a 0 because it gives us 0 for that. Factor theorem. Here's the other one that we're looking at in this lesson. Remainder theorem. Let's just take a different equation. Let's make one up. F of x equals 2x to the third minus 4x squared plus x minus, let's say, 15. Just give it a nice number. I keep getting that crooked on the screen, don't I? 2x to the third minus 4x squared plus. So we just took this equation. We said, okay, let's see if -2 is a factor here. Actually, since this is a -15, let's try -3 because 2 probably would not be a factor since we know this is an odd number. So let's say we're going to figure out if x plus 3 is a factor. So we can divide -3, since that's a plus 3, into 2, -4, 1, and -15. Wait, let's do this at the same time. If I just substitute -3 in, 2 times -3 to the third power minus 4 times -3 squared plus -3 minus 15. Trying both methods, right? I can just substitute it in and solve, or I can do division. I'm going to do this one first. -3 to the third power. -3 times -3 is a positive 9. and times another negative 3 is a negative 27. So 2 times negative 27 is negative 54. Negative 3 times negative 3 is a positive 9 times a negative 4 is negative 36. Minus 3 more. Ooh, that's just going to be a big negative, isn't it? So negative 54 minus 36, negative 90, 93, minus 108. So this says negative 3 is not going to be a factor. Let's see what we get by synthetic division. Negative 3 times 2 is negative 6. Add those together. Multiply that. That's a positive 30. Multiply that. Negative 93. Add those together. Negative 108. We have a remainder, which is the same thing we found here. Shortcut. C. Negative 3 is not a solution, not a zero. So that means x plus 3 is not a factor. And why? Because of the remainder theorem. If there is a remainder, highlight all the important stuff here. The factor theorem says if the remainder is 0, then this is a factor. The remainder theorem says if you have a remainder, it is not a factor. It is not a solution. It is not a 0 for the equation. So these kind of go hand in hand because both of them check to see what is the remainder or what number do you get when you substitute this in. Same thing, same number, right? You get the same number either way, whether you substitute in or whether you use synthetic division. Or if we'd have done long division, we could have done long division if we wanted to also. We would just divide by the original term. We'd still get the same remainder. So factor theorem, remainder theorem, they kind of go hand in hand. But that's what they tell us. Okay, is there questions on that? Does that kind of make sense so far? We had the fundamental theorem of algebra that tells us how many zeros this has. All right, and that's just looking at the largest exponent. Very simple. What's the largest? There was a sixth, there's a third. We don't care about those. They're not the largest one. The eighth was the largest one. That tells us there's 8 solutions. Now remember, some of those might be imaginary numbers, imaginary zeros. Then we had the factor theorem that says when we get a remainder of 0, that means that this is a 0. This is a factor. This is a 0. If we get a remainder, theorem says if this is not 0, then this is not a 0 of the equation. This is not a factor of the equation. That doesn't work. All right, let's see if our curriculum adds anything else to that. It was discovered through factoring the binomials x plus 2, x plus 9 were factors. You can do synthetic division and figure that out. We're not going to watch the whole video, but let's jump to the fun part. Here's they took x plus 9. So they took the other one. We divided by the x plus 2. And they found a remainder of 0. And that says, oh, x plus 9 is a factor. Negative 9 is one of the zeros. Right? So that was according to the factor theorem. And it says, what about the other? How about the binomial x plus 1? Is that a factor? So they tried dividing the negative 1 in there and got a remainder. So the factor theorem states that a first degree binomial is a factor of a function if and only if the remainder is 0. If and only if. I like that. That's a math thing. So that's the only case in which we can say, yes, this is a factor. That the x plus 1 is a factor if and only if. There's no other way it is. But this is not. So it says, is x plus 12 a factor of the function x squared plus 6x minus 72? Well, we would have to have a remainder of 0, right? So they go through the whole portion of the synthetic division, dividing by negative 12, bringing the 1 down, multiplying times negative 12, adding that to 6, and then you have negative 12 times negative 6 right there, which will be positive 72, and you add those together and get 0. So that says, yes, x plus 12 is a factor, according to the factor theorem. And then there's another example for the factor theorem if you would like one. But I think you guys have got this. I think you understand what the factor theorem says. Anytime you get a remainder of 0, it is a factor. And then the remainder theorem on this page, 2 theorems down, 1 more to go. The fundamental theorem of algebra tells us, let's look at that the number of zeros of the function, so that's the fundamental theorem, that's the first one we talked about. The number of zeros of the function is equal to the degree of the function. So we know x squared will have 2 solutions because that's the largest exponent. And we know that if the zeros are applied in synthetic division of negative 2 and negative 9, the factor theorem says the remainder is going to be 0, which it was for those. And what happens when they substitute? This is where I was showing you the other method. We could just substitute into the negative 2 and you'll still get the same 0. So that's why I was showing you that shortcut. There's another way to do it other than synthetic division. They could do it with a negative 9 also, since that's also. It says, refresh your memory about what happens when a function is not a factor. You get a remainder. So when the opposite of the constant term of the binomial is substituted in x for the function, the result is equal to the remainder when the function is divided by the binomial. This is the remainder theorem. This theorem itself will help you determine whether or not a number is a 0 of the function. When the remainder is 0, it is a function defined by the factor theorem. So the remainder theorem is, takes care of all the cases when the factor theorem is not true. Okay, so this just talks about the different ways we talk about these things. If you have a polynomial and a number a, if x minus a is a factor, then a is a 0, right? So if x minus 1 is a factor, then 1 is one of the zeros. And you can prove that by long division, synthetic division, factoring. If it's a 0, that's where the graph crosses the x-axis, and you can substitute a into x minus a, and it'll equal 0, and you can substitute it in f of x, and it equals 0. So, and here's another example. Find the remainder when you divide this equation by x plus 10. So they did it by synthetic division first, and they did it by just substituting the negative 10 into the equation. And either way, they get 6 as the remainder. So that is the end of that lesson. There are some practice problems. There are some practice problems for you to go and try this. Find the zeros of each function and then drag which one of those. One of these has a negative 2 as a 0. So you'd have to get your paper and pencil and take negative 2 and divide it into this one, and divide it into this one, and divide it in this one, or substitute it in for x. Remember, it's the same thing, synthetic division or substituting in for x. And then you drag it to whichever one's correct. Right? I'm going to guess it's that one. Nope, it's not. It must be the middle one. Oh, yeah, because the x plus 2. X plus 2. So we know it's that one. Then there's some more down here. Is x plus 3 a factor of this function? So substitute it in or do synthetic division or however you like. But it says no, it'll get a remainder. But there's 3 problems down here. This one has several there. See the practice problems on the next page. Activity 1 has 8 right here. Woo! How many? Oh, this is simple though. According to the fundamental theorem of algebra, how many zeros should we expect to have? 2x to the 5th. That guarantees there are 5 zeros. It does not guarantee they're all real. It just guarantees there's 5 of them. Submit. Yes. Next one. Oh, this one says determine the zeros. What's the zeros of this? Yeah, and there's 8 problems there. Then there's activity 2. Determine if this is a factor. Is x minus 6 a factor of this? Check your work. And there's more problems down here. So there's 3 problems there. All right, let's go look at the assignment for this first lesson. According to the fundamental theorem of algebra, how many zeros? Which of the following is a 0? and it gives you factored form. We like factored form. Is x minus 8 a factor? Find the remainder. Find the remainder. Okay, so there's 5 problems. Give you a good roundabout look at it. Now, all right, now we can look at the next lesson because we want to look at this next lesson. We're going to look at the rational root theorem and Descartes' rule of signs. These are really cool. These are really cool. So when you make a new car purchase, right, a buyer will search for a make and a model within the price range. Right? Okay, I don't want to spend more than $15,000. So I'm going to go to my local dealership, my own local car dealer. I'll take a test drive, but I'll just look at cars that are like $15,000 or less. And that's how I'm going to narrow it down. If I want to purchase a dog or a cat, first you're going to decide what breed of dog do you want, right? What breed of dog? Or am I looking for a Siamese kitty or something? Then I'm going to go to a local animal shelter or a pet store or a breeder, and I'll play with the animals and see which one just really seems like that one's mine, right? If I want to get a house or an apartment, first I'm going to, I might look and say, well, there's houses all over Benton County. It's like, no, I don't want to live anywhere in Benton County. I just want to live like in Centerton, or I want to live in Bentonville. And so I'm going to narrow it down and say, oh, and I don't want to spend that much money. I don't want to spend more than $250,000 to buy a house. I don't want to buy an $800,000 house. So that'll narrow it down to which neighborhoods that I'm going to look at in those towns. Then I'm going to get a realtor to let me go in and see the houses, right? So you will use different criteria and not search every house in Benton County. You're not going to go take a tour of every house for sale in the whole county. You're going to narrow it down and say, okay, I'm just going to look at these possibilities, right? So those possibilities are based on price, location, other preferences, and then you'll make a decision. Well, we can do the same type of thing with polynomial functions. So we're going to learn, what does the rational root theorem and Descartes' rule of signs indicate about the zeros? And how can the zeros in end behavior allow a graph to be sketched? We've actually looked at the graph to be sketched part. So we're going to look at this nice, big, long function right here. Let me get another piece of paper because we need another piece of paper to get on this one. Okay, look at that baby. So how many zeros does this equation have? I'm seeing a 5. Right, we know there are 5 zeros. We know there are 5 zeros because it is a 5th degree polynomial. Now we want to find them. How are we going to start? Mr. Brock, I don't know how to factor a 5th degree. No, I don't know how to factor a 5th degree either. So we're not going to factor it like we have the quadratic formula. If it was a quadratic, it's not a quadratic. There's lots of ways to factor things, but we don't have any rules on factoring a 5th degree. The only way that we know to find a factor is to divide and see if the remainder is 0. Right? If the remainder is 0, hey, we found one. But where are we going to start? What numbers are we going to divide? It's like, well, let's see. I guess we could start with 1 and see if that one's a factor. Okay, well, let's start with 1. Let's do synthetic division. Make this a lot easier. So we have a coefficient of 1, 2, -4. Oh, another -4, -5, -6. Okay. Multiply 1 times 1, add 1 times 3, add 1 times -1, add 1 times -5, add 1 times -10. Okay. So checking 1 was not a factor because the remainder theorem says that's not 0, so it's not a factor. Well, okay, let's try -1. So we'll add that to our list. -1. 1, 2, -4, -4, -5, -6. Bring that down. negative 1. 1 times negative 1. Add those together. That's a 1. So again, negative 1. Add those together. Negative times a negative. Now we've got a positive. So that's going to be a positive 1. Multiply those together. That's a negative 1. 1 times negative 1. That's negative 6. Negative 1 times negative 6 is a positive 6. Oh, there we go. There's 1. That works. Okay, 4 to go. So what are you thinking? Are you thinking this may take the rest of class just to find the other 4? How many numbers are we going to have to check before we find all the 5 factors? What if one of the factors is a half or 2/3? We're not even checking those numbers yet. So we'll have to check 1, negative 1, 2, negative 2, 3, negative 3, 4, negative 4, 5, negative 5, 6, negative 6, 7, negative 7. We could be checking all day long to find the 5 factors, especially if it turns out that some of them are imaginary. We don't even know if they're imaginary. We need more help to solve this problem. Okay, well, that is where the rational root theorem is going to come into play. Now, they did the same thing. They started with 1. All right, let's check 1. Let's do the synthetic division. And they're going to do all the way through. Let me get to the end here. Just like we did. And they found out that 1 did not work. Had negative 16. And it would be very time confusing to test every real number to find the 5 solutions. All right, well, let's talk about the rational root theorem. I'm going to cut that off for the moment here. Put this in our notes. Rational root theorem. Okay, let's see what the rational root theorem says. The rational root theorem says we don't have to check every number out there. We don't have to check every number out there. You're like, thank you, rational root theorem, because I need some help. I'm a little overwhelmed by how many numbers I'm having to look at here. The rational root theorem says, all right, we're going to look at the coefficient of the largest term first. Q. And what is the coefficient? Is 1. So it says, okay, what are the factors that multiply together to be 1? Really, there's just plus or minus 1, right? 1 times 1 or negative 1 times negative 1. Okay. Then it says, let's look at the constant at the end. We'll call it P. P is negative 6. What are the factors of P? Let's see. 1 times 6 and 2 times 3. Plus or minus, right? Whether it's a positive 1 and negative 6 or negative 1 and positive 6. So the factors are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. 1, 2, 3, and 6. That's the only possible numbers that can multiply together to be negative 6. So the rational root theorem says if we take all the P's over all the Q's, this is the only possible numbers that could be zeros. You're like, whoa, what are you talking about? Okay, let's take every P and put it over every Q. Now, Q is just 1. Q is just 1. So the bottom's just going to be a plus or minus 1. So that's not going to change our numbers. That really simplifies things. So the only possible numbers could be plus or minus 1 over 1, plus or minus 2 over 1. So it doesn't change anything. Plus or minus 3 over 1, and plus or minus 6. So the only numbers we'd have to check would be 1, negative 1, 2, negative 2, 3, negative 3, and 6, negative 6. That's it. That is the only numbers that we have to check. 8 numbers. And hopefully 5 of them are zeros, unless some are imaginary. Again, if some are imaginary, we won't even find 5 out of that. But there's no need to check 4 and -4 and 5 and -5 and 7 and -7, any other numbers like that, because the rational root theorem says this is the only possible numbers. P over Q, all the factors of -6 over all the factors of 1. I like it when it's all the factors of 1, because that just means whatever this is the only possible answers we have. All right, well, that's helped a lot. Now we can just do synthetic division by 6 more numbers. Like, are we going to do that? Let's do at least 2 more. Let's do 2 and -2. So 2 into 1, 2, -4, -4, -5, -6. Bring down the first term. 1. That's 4. 2 times 4 is 8. That adds together. 2 times 4 is 8. That adds together. 2 times 4 is 8 again. Well, we get a lot of those. This is 3. 2 times 3 is 6. Oh, look at there. 2 is one of our solutions. Nice. How about -2? Let's do -2 differently, just to show that the other way works as well. -2. Let's do -2 to the 5th plus 2 times -2 to the 4th minus 4 times -2 to the 3rd minus 4 times -2 squared. I'm going to run out of room. Minus 5 times -2 minus 6. See, I just substituted -2 in. I could have done synthetic division. Maybe that would have been easier, but I just took this and I put -2 in because it should work the same way. So that equals -2 to the 5th. Since it's -2 5 times, it's going to be, oh, wait. Yeah, it's going to be a negative number, right? So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that's -32. To the 4th power, that's going to be a positive number. -2 times -2 is 4, times -2 times -2 is 16. So plus 32, because 2 times that. -2 to the 3rd power is -8, right? Times -4, that's another positive 32. -2 times -2 is a positive 4, times -4 is minus 16. -5 times -2 is plus 10, and then we have the minus 6. So these canceled out, -32 plus 32. Then we have 32 minus 16 is 16, 26. So this equals 20. So -2 is not working. All right, let me use a different color to cross it out. So this didn't work, and that didn't work. So far we found 2 of the 5, and there's only 4 left. What if I told you we can narrow it down even more? Would that make you happy? Yeah, it'd make me happy. Let's look at our last theorem we're looking at today. Descartes' rule of signs. So here's what Descartes figured out. He said, if we have this polynomial, we can determine how many possible solutions it has. We know it has 5, but we can narrow it down even more than that. Okay, so he says, all right, this is a positive, right? So what happened here? It's still positive. We're just looking. I'm sorry, I'm going to get this up centered. I need to turn this camera or something because I keep angling it. We want to see how many times the sign changes. I'm going to add the word changes up here. Did not change. Oh, this goes from a positive to a negative. There's one sign change, positive to a negative. Negative to a negative. negative to a negative. So there's only one time that the sign changed as we started from left to right. Started as a positive, stayed a positive, changed to a negative, stayed a negative, stayed a negative, stayed a negative. So this has one positive 0. That's it. Since the sign only changed once, there's only one positive 0, which means right now, since we found 2, we don't have to check 3 and we don't have to check 6 because there can't be another positive solution. We already found 2 was a positive number. This was a negative number, so that didn't help us. 2 is a positive number, so that means 3 or 6 can't be, because Descartes said there's only one positive 0 even possible. You're like, oh, that is so cool. Now all we have to do is check those 2. Now I see a problem there. We found these 2, and there's only 2 left, and they're supposed to have 5 zeros. Oh, that guarantees we've got some imaginary solutions. Because if these 2 both work, that's only 4. That's not 5 solutions. I also already know something else. One of those is not going to work, I guarantee. One of those will work, guaranteed. How do you know that already, Mr. Brock? Well, let's finish Descartes, and then we're going to talk about the other thing that comes into play here. Descartes can also tell us how many negative zeros it can have by doing this. Substitute negative x. If we want to know the negative zeros, we've got to substitute negative x. So this would be negative x to the 5th plus 2 times negative x to the 4th minus 4 times negative x to the 3rd minus 4 times negative x squared minus 5 times negative x minus 6. Okay, so negative x to the 5th power. So that's negative x times negative x times negative x times negative x times negative x. Well, negative x times negative x, this would be a positive, right? Because negative times a negative. And this one, negative times a negative, would be a positive. And then a positive times a positive would be a positive. But then we have 1 at the end, that's a negative. So this will end up a negative because it's an odd number of x's. So this will simplify to negative x to the 5th. Plus 2 times negative x to the 4th. Well, negative x to the 4th is going to be a positive x to the 4th. Negative x times negative x is positive x squared, positive x squared. So this will be plus 2x to the 4th positive, because it's an even number of negatives. This one has an odd number of negatives. Negative x times negative x times negative x. So that's going to be negative x to the 3rd times negative 4. So that's going to be a positive 4x third, because it's a negative times a negative. This one is x squared, positive, because negative x times negative x is a positive x squared times a negative. So that's a negative 4x squared. Negative 5 times negative x is positive 5x, and this is minus 6. So after we substitute negative x in and simplify, let's do the same thing we did up here. Negative, positive, there's a change. This did not change. Positive, 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 negative, there's a change. Negative, positive, there's a change. Positive, negative. For possible negative zeros. Okay. Well, here's the nice thing. If we have 1 positive and 4 negative, that's 5. We expect 5. But the only thing this can't tell us is how many of these are going to be imaginary. Here's the important thing you need in your notes about imaginary zeros. Imaginary zeros. Oh, and I'm going to write this in red in capital letters and underline it. Always come in pairs. Always. Always, always, always. We will never have one imaginary solution. If there's one, it has a complex conjugate. It has a partner. Imaginary numbers are very, very timid. They're very anxious. They're very shy. They won't go anywhere by themselves. Imaginary zeros, imaginary solutions always bring a buddy. They always, always, always come in pairs. So that tells us something. So here, I'm gonna add on to my paper. I need more paper here. So for this equation, here's the possible solutions. Okay, so for positive, for negative, and for complex, which is imaginary. Okay, solutions. Solutions. I'm going to make a table of possible. We know there should be 5 altogether, right? There should be 5 solutions. Descartes said there's 1 positive. Okay, well, that one would guaranteed. Said there could be 4 negative zeros. In that case, there would be 0 imaginary solutions because we've already found all 5. Okay, so that makes sense. That's great. Now, however, we know, because what we've checked already, we know there's not 4 negative ones because there's not 4 left. There's 1, there's -3 and -6. And we haven't checked -3 and -6, but we know -1's a solution, but we know -2 is not. So it's like there's not going to be 4 just because we've already checked. So another possibility, we know there has to be 1 because it couldn't be imaginary because it would be by itself. And it comes in pairs. But maybe 2 of these are imaginary. So anytime you can subtract 2, that's another possibility. This could be the makeup. Maybe there's 1 positive, 2 negative, and the other 2 are imaginary. But there's still one other possibility for this one. There's going to be 1 positive guaranteed. Maybe none of these solutions are negative and all the other 4 are negative. Imaginary, I'm sorry. That's it. That's the only possible solutions. There's definitely 1 positive because there's not a pair of them that could be imaginary. If this was a 2, it could be 2 or 0. But it's not 2, it's only 1. So we know there's 1 positive solution, and we know we've already found it. It's 2. That means we didn't have to check 3 and 6. There could be 4 negative, according to Descartes. Could be 4 negative. But that means it could be that a pair of them are imaginary, or it could be 2 pair of them are imaginary. So these are the ways you have to look at it. You got to figure out how many possible positive and negative, and generally that's going to be the total number of solutions. There could be all 5 solutions. But if there's a pair of imaginary solutions, where does it come out of? It can't come out of the positive because there's not a pair to pull out. There's just not. We can't pull a pair out, but we can pull a pair out of here, or we could pull two pairs out of here. So what this helps is if we check -3, and let's say I'm not going to check it, but let's just pretend that, hey, this one works too. We're done as far as finding real solutions, because that gives us two negatives. Here's one, here's one. We can't have three negative solutions. It's not possible. So we could go ahead and say, okay, we know it's not -6 because I already found two negative solutions. I found one positive, I found two negative. So that means there's two complex. And we're not going to worry about those. That kind of makes sense? Is there questions there? I don't want to totally lose you on that. But all of these work together. The fundamental theorem of algebra tells us how many solutions we're looking for. The factor theorem and remainder theorem tells us when we found one of those solutions. Right? If it's 0, we found it. If it's a remainder, we haven't. The rational root theorem tells us, well, here's the only ones you have to check. You just have to check these 8. You don't have to check every possible number out there. And then Descartes says, oh, well, after you found one, you're done with all the positives. You don't have to check any of the other positives. Or if you found 4 negatives, you're done. Or could be 2, or could be 0, because it might be some imaginary pairs. So it's really kind of wonderful how all 5 of these work together to help us take a big, long, nasty polynomial of a high degree and start narrowing it down to where we could reasonably solve that without spending all day checking every possible answer. Let me look at here. They have another one here. So here's where they take the factors of 6 and the factors of q, and they put all the p's over the q's, and it's just the factors of p, because since this is 1, it's just plus or minus 1, 2, 3, and 6. And here they check all 8 of them. They did the division for every one of them to check every one. 6 was not. -6 was not. -3 was. That was our other one. -3 and -1. There was the two negatives, -3 and -1. 1 didn't work, but 2 did. So the 1 positive and the 2 negative. They checked all 8 of them. It says, the function is guaranteed to have 5 zeros. What happened to the other 2? Think about that. Well, they're imaginary. We'll go ahead and break the spell on that. I want to look at another example before we get it. Let's see, the rational root theorem is just the example I want. No, why does it think I'm not logged in? Okay, for whatever reason, it won't let me look at that. If I reload the page, I need to reload the page, period. It won't even let me look at the next page. Let me reload the page. Let me look at this now. Yeah, now let's look at this. Yay. Okay, we want to do this one here. And I'll just do it on paper because it doesn't always show as much doing it on the screen. We're just going to find the possible factors. And we're not going to find the zeros, and you're going to be happy we don't. But we're going to learn what kind of zeros we'd be looking for and what could they possibly be. P's and Q's. P's and Q's. Q, P. So the possible P's, 1 and 11, well, that's it, right? There's no other factors of 11. 1 and 11 is all there could possibly be. Q's, 1 and 3, plus or minus 1, plus or minus 3. So that's the only possibilities. So if we want to check for solutions, put P over Q. It could be, let's start with P being 1. It could be 1 over 1, which is just 1, right? Or it could be 1 over 3. So it means it could be plus or minus 1/3. That's a possible. Those are 4 possible zeros for this equation. So that's all the P's. Now let's look at the 11s. I mean, it's all the ones. Let's look at the 11s. So it could be plus or minus 11 over 1, which is just 11. Or it could be plus or minus 11 over 3, 11 thirds. So if you're going to start doing that synthetic division, woo, we're going to have some fun with that, right? We're going to have synthetic division with a fraction. But we won't. We're not going to find the zeros. But let's find out how many. We found there's 8 possible in this one. There's only 3 total, right? Let's use Descartes' rule and find out how many possible there are. Positive, 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 negative. One sign change. So there's one positive, 0. One positive, 0. That's it. Once we find which one of these, 1, 1/3, 11, and 11/3, whichever, once we find one, we don't have to check the rest. If we guess really good, we could find it on the first shot, right? But we'd probably take 2 or 3 of them before we'd figure it out. Now let's check the negative possibility. 3 times negative x to the third plus negative x squared plus 21 times negative x minus 11. So this is going to be an odd number, so that's a negative. So this will be negative 3x to the third. That's going to be an even number of negative x's, so that's a plus x squared. Negative x times positive 21, and then negative 11. So it changed here, it changed here. This one did not change. So 2 possible negative. I didn't put possible there because if there's only one, there's guaranteed to be one. So the solutions, positive, negative, or imaginary, we know there's 3 altogether. So it could be 1 positive, 2 negative, and 0 imaginary, or 1 positive, 0 negative, and both of them are imaginary. So this is our possible solutions. All 4 of those negative numbers are not going to be a solution. Only 2. And if we find 2 of them, if we're going through there, and if we find one, all right, we're going to find a positive one, and we can stop. If we find one negative solution, we know there's one more, because there has to be 2. 1 is not a possibility for negative solutions. But if we check -1 and we check -1/3 and we check -11 and none of those work, there's no reason to check this one. 0, 0, 0, 1. That would be one negative solution, which is not a possibility. So that's where Descartes really helps us. We don't have to check all 4 of those necessarily, because if we find 2 of them right off the bat that are both negative, we can stop because we know there's not going to be more than 2. If we check the first 3 and none of them are there, we know there's not going to be one negative solution. Let's go to page 2. Wow, that was page 1. Oh, this goes over Descartes' rule signs, which I've already covered with you. So I'm like, wait a minute, we're not that far behind this lesson. Oof, all right. Find the number of possible positive real zeros by checking the sign changes. Positive, positive, negative, negative, only one sign change. This is that x to the 5th that we did first. Then make it negative. Substitute negative and simplify. Find the possible number of negative ones. There's 1, 2, 3, 4 sign changes. So that says could be 4 sign changes. So it could be 2, could be 0. So they made their little chart. The one positive is guaranteed because it can't be imaginary if there's only one of them. But it could have 4, could have 2, could have 0, which means the complex 0 is going to fill in the missing zeros. All right, page 3. We looked at all that on paper already. Here's another one. Determine the possible number. Here's a video. We don't really have time to watch it, so you can watch that. If you're still confused about Descartes and how to figure out the possible positive, negative, and complex zeros, here's a 4-minute video that will take you all the way through it. And here's another video where, let's see, this is where she looks at it. And what did she do with this one? Oh, she was finding the possible P's and Q's. Well, 5 minutes. Okay, this will pretty much wrap up class. Let's see see if we're missing anything here. Sketches. We already talked about sketches from zero. Making a sketch based on the zeros. Okay, so we're going to watch this last video right here.
Hello, today we're going to look at the rational root theorem and Descartes' rule. Here we have our polynomial function, and we're going to find our possible roots first. We're going to look at p, which is the constant, and we're going to look at q, which is the leading coefficient. We're going to list all the factors of 9, which in this case is positive or negative 1, positive or negative 3, and positive or negative 9. And we're going to list all the factors of 2, which in this case is positive or negative 1, and positive or negative 2. Then we're going to go ahead and divide p by q, which means I'm going to take each one of these factors and divide them by each one of these factors. So the first one is going to be positive or negative 1 divided by 1. And we have positive or negative 3 divided by the 1. And positive or negative 9 divided by 1 as well. Now we're going to do the same thing but with the 2. So I got positive or negative 1 over 2, positive or negative 3 over 2, and then positive or negative 9 over 2. Our next step would be to use synthetic division to figure out which one are our roots. But before we do synthetic division, we're going to go ahead and use Descartes' rule to figure out our possible roots. So if I have 2x to the 4th plus x to the 3rd minus 19x squared minus the 9x plus 9, I'm going to see how many times the sign changes. Well, the first one doesn't change. The second one, there is a change. Then we have no change, and then we have another change. This means that I have 2 or 0 possible positive roots. Now I'm going to repeat the process, but this time I'm going to plug in a negative x. So this is going to be 2 times negative x to the 4th power plus a negative x to the 3rd power minus a 19 negative x to the 2nd power minus a 9 times a negative x plus 9. If I simplify this, I'm going to get 2x to the 4th minus x to the 3rd minus 19x squared plus 9x plus 9. So now I'm going to go ahead and see the sign changes. I have one sign change here, no sign change here. I have another one here, and none there. That means I have 2 or 0 negative. So to determine the complex roots, I'm going to go ahead and make myself a chart. And what I'm going to do is I'm going to determine how many possibilities I have between my positive and negatives, which means I can have either 2 positive with 2 negative or 2 positive with 0. So you got to match each one. So we got 2 positive with 2 negative or 2 positive with 0. And then we'll repeat the process. With 0, we got 0 positive and 2 negative, 0 positive and 0 negative. So to find the complex roots, we go back to the degree of our polynomial, which is 4, and we have to make sure that we add them across and they equal 4. So 2 plus 2 is 4. That means there's a 0 complex. 2 plus 0 is 2, which means I have 2 complex. 0 plus 2 is 2, so I have 2 complex. And 0 plus 0 is 0, so that means I have 4 complex. Now I'm going to go ahead and use my synthetic division to see if I can find one of my roots. So I'm going to go ahead and start off with the negative 1. So I have my coefficients, which are 2, 1, negative 19, negative 9, and 9. And I'm going to go ahead and start off by bringing my 2 down. 2 times negative 1 is going to be negative 2. So 1 plus negative 2 is going to be negative 1. Negative 1 times negative 1 is going to be a positive 1. And negative 19 plus 1 is going to be negative 18. Negative 18 times negative 1 is going to be a positive 18. And then negative 9 plus 18 is going to be 9. And then 9 times negative 1 is going to be negative 9. And 9 plus negative 9 is 0. Which is good news because that means that negative 1 is one of our roots. So this is where we can use Descartes. Because when we did Descartes, it said that we could either have 2 or 0 negative possible roots. Well, if we have 1, that means we have to have one other one, which means that we can get rid of the 0 because that's not one of the possibilities. And then you can go through and go ahead and use any one of your other possible roots with synthetic division to find the remaining roots. And that's how we use the rational root theorem.
She narrowed it down already to just a smaller number there. Man, I wish we had more time because this is a lot of fun because these all work together so beautifully to take these big x to the fourth, x to the fifth, x to the seventh equations and be able to narrow it down and actually find solutions in a somewhat reasonable amount of time. I mean, it may take us half an hour, but with an x to the seventh, you'd think it'd take you 7 hours, right, to find all the solutions. So really cool stuff today. I wish we had more time. Go back and look at some of the examples that we didn't look at. Go in there and watch some of the videos we didn't watch just to help you understand. But when you go to the assignment, if you get lost, don't just guess. Go back and look and see if there's some examples that help you that we did not get to today, because there's lots of good examples in there and lots of way to look at all of that. But fun stuff. Whew, like I said, we were busier than a one-legged man in a butt kicking contest today trying to cover all this material, but we made it. We got pretty much through everything. We just had to skip some of the examples which were repetitive, but we hit everything that we wanted to hit today. So all right, like I said, unfortunately, since Thursday is PSAT testing and work keys, this is our only class we have this week. So if you have problems, you can email me and I'll try to get back to you, or we can set up a meet time or something sometime other than Thursday. And then we do have the parent teacher conference going on Thursday night. So guys, have a great week. It's a busy one. We'll see you next week.